everyone. Today we have a special guest coming directly from Brazil. We have Gabriel Coutinho from Federal University of Minas Gerais. He's been working combinatorics and applications in quantum stuff for a long time and collaborating for very long with Crystal from KDB. So welcome also, Crystal. I think the first time IS. Feel free to come more. And he also started working in deep stuff also since last year. And he's going to talk about his, I think, main topic with combinatorics quantum walks. Thanks so much for coming. And
Thanks.
you press OK.
Oh, yeah, okay.
Yeah.
Yeah. Still working. Okay, thanks, Fernando. Thanks for having me, for the invitation. Thanks all for coming. So at first, when Fernando invited me to give the seminar, I was like, oh, great. So I'm going to talk about our joint work in progress. It's like, no, don't talk about work in progress. It's going to be recorded, it goes to YouTube. Talk about the stuff you already have published. I was like, okay, then. So as Fernando said, combinatorics and quantum walks have been my main line of research for a while. And but of course, I know most of you probably haven't heard about quantum walks before or worked on quantum walks, I suppose. So yeah, so I prepared the talk, which is mostly very introductory, not so much math, try to actually motivate you to at least think that this is interesting. And the starting point is every time someone talks about quantum walks, they say, well, this is the quantum analog of a random walk. That's I've put this sentence in the beginning of grant proposals, maybe more than I should. And then the question is, what exactly does this mean? I mean, what is a quantum analog of a random walk? I mean, random walk is probably something you've encountered before, and here everything happens in a graph. So this is like a graph that I just drew, and then a random walk. I mean, you're starting in this black vertex here, and then if you simply start hopping to neighbors, then this is pretty much what's happening. Of course, it could happen in different ways if you repeat this experiment many times. And then what really matters when you think of a random walk is the probability distribution, right? So the probability distribution of a random walk is going to pretty much tell you that if you're here, then you have a, let's say, 25% chance of ending up in any of the neighbors, and then you keep moving forward, and then this probability sort of accumulate. And usually you're interested in questions such as how long does it take to have certain minimum probability somewhere in the graph? What is the to what does this converge? I mean, what is the stationary distribution? I mean, these are usually the questions you have when you're asking about random walks, right? I mean, how does this process occur when you take into account the probabilities? Because of course, I mean, if you focus on one particular experiment of your random walk, then you don't really get so much. Now, what exactly means when you say the quantum analog of this process, right? So this is another example of a random walk, just to like put a more random looking graph. So we sort of like get a feeling of what's happening here. This is all classical, right? And I mean, these are like some, I don't know, 12, 13 steps. And the thing is very quickly converging to this sort of like everything is shaded gray, sort of like saying that there is a sort of like, I don't know, similar probabilities of being pretty much anywhere. This tends to be the case actually for random walks in pretty much any sort of graph. I mean, it doesn't matter where you start, it's going to converge to this stationary thing, which tends to be sort of like similar everywhere, except if the graph is bipartite. And when I say bipartite, this is what I mean. You have two sides. Can I? Yeah, I can actually do that. You have two sides, and then there are nothing connecting here, these vertices. So these vertices are all not connected. Same thing on this side. And then if the graph has this property and you start in one side, then of course, in the next step, you're forced to be entirely on the other side. And then on the next step, you have to come back So the thing is not going to converge to a stationary, because at every step, if it's an odd number of steps, you're on the right, an even number of steps, you're on the left. So the thing actually keeps moving back and forth. It is going to converge in this on each side. It's going to like sort of look at this. It's going to start looking more like a stationary thing on the entire side. But again, you're going to be moving back and forth. So if the graph is bipartite, this is what happens. If the graph is not bipartite, and this is an example of a graph which you cannot separate into two sides, then random walk in the graph sort of looks like that. Okay. So again, what is the quantum analog of this process? Yeah, so this is now first I'm going to show you what the quantum walk could look like, and then I'm going to try to explain a little bit what could be going on. So this is the analog movie of a quantum walk. So of course I'm going to explain what this shades of gray mean. But the first thing you could notice is if I repeat this, it sort of looks like the thing is not really converging to a stationary thing. It's sort of like moving back and forth, oscillating a little bit. So this is the first big difference between quantum and classical in this setting, is that a classical random walk usually converges to a stationary distribution, whereas a quantum walk never does. Okay.
But can you explain what
I
you're
will.
talking about? Because I mean, what are these
Yes.
notes?
Yes, I will. Yeah. It's coming. Yeah, of course. I'm saying what is going to happen. Yeah, of course I'm going to explain. But just before doing that, this is what a quantum walk would look like in those two other examples. Just so we see, like here again, the thing is sort of like moving back and forth, and then here, as opposed to what happened with the random walk, the thing actually doesn't really stays in each side in different steps. It sort of like goes, I don't know, gray everywhere. Okay. Now, what does this mean? Of course, I mean, what's happening here? So this is my graph again, and what does blacks and whites mean? This means that each one of these vertices is representing what we know as a qubit, a quantum bit. And physically, you can think of a quantum bit as, I don't know, the spin of an electron, or the polarization of a photon, or many other different realizations. Mathematically, a quantum bit, you can think of it as a two-dimensional vector space over the complexes, okay? And any one-dimensional subspace is a valid state. So you're basically thinking on a C to the 2, and then you have subspaces, and then if this is evolving in time, then you can think of it as a line, sort of like moving in space. This is the state of a qubit evolving in time. And then when I put these whites and blacks, what I actually mean is that this qubit is being initialized in the state given by this vector 0, 1, and the whites are all initialized in the state given by the vector 1, 0. I'm using here the direct notation. Some of you might have seen before, but some of you might have not. This is just a different way of writing very simple two-dimensional vectors.
So you're not considering superpositions?
No, the initial state is this. So the quantum walk is the system evolves according to a quantum process, and then things become entangled, actually, here in superpositions of different states. So that's basically what was happening. Yeah. Here I have 9 vertices, so 9 qubits. And then the axioms in quantum mechanics, they will tell you that this entire thing is also in one particular state, and this state is the Kronecker product of the states of each one of the individual qubits. So this is a two-dimensional vector, so this big thing here is going to be a 512 dimensional vector because we have 9 qubits. And then you take this chronicle product, which is sometimes conveniently written in this form just to save some, like, you don't need to write all the signs. And then this is the state of the system. And then the quantum walk is what this, what is going to happen with this state when you simply leave this system and let it go with time. Okay. So when you see something that looks like that, this basically means that each one you would want, if this is like a simple analog of a random walk, you would think that after a while each one of these qubits is itself in one particular state, but that's not actually what's happening here. So if each one of these qubits were in one particular state, which is given by a two-dimensional vector, then the state of the whole system would be the tensor product of each one of the individual states. But this is not happening. This is, if this were the case, then these guys wouldn't be entangled. But what actually happens with the quantum walk is that they become entangled. So now, to be more precise, that particular state, which is, can I use this pointer? Oh, this thing actually doesn't.
Sorry, before you continue, I'm a little confused. So
Yeah.
for the classical random walk, you put it on the graph, you start in one point and you're trying to just randomly understand what's happening.
Yes.
But here you're putting dynamics on it. You're trying to tell me that the random walk, it's evolving with some specific quantum process. It sounds like you're telling me what the process is, rather than being a total random exploration of states. You see what
it is? It is determined by the edges, if these edges have a particular physical meaning. So when I say that I have qubits such as these, and then there is an edge between these two, and there is no edge between these two, what this actually, I was not actually planning to go into this level of detail, but what this actually means is that there is a Hamiltonian acting on the system. And this Hamiltonian is pretty much putting some energy between these two guys, but nothing between these two guys.
Then I understand.
Yes.
In the classical random walk, there's no discussion about Hamiltonians.
Well, the Hamiltonian would be
of the graph.
But see, there's still the edges that allow you to move and the non-edges that don't allow you to move. And so you could think of this as a sort of like in the random walk, the Hamiltonian that tells you that allows you to move or not move.
Okay, so
right.
When you're discussing here Hamiltonian, you kind of mean you're trying to put the structure of
yes.
Okay.
Yes, the Hamiltonian.
So it's not that you're putting dynamics on the system. It's more like
the Hamiltonian is determined by the graph. Yes, okay. Or the graph is determined by the Hamiltonian. Yes.
So fixing the Hamiltonian fixes all these alphas.
No. Wait a second. I'll get there. Fixing the Hamiltonian fixes the edges.
Okay.
How? What happens with as time evolves? Then you have to solve Schrödinger's equation. You get a matrix, and for each time t, you're gonna have different alphas.
Yeah. So they are uniquely determined given the number
and the time,
right.
and the amount of time you waited. So this is after time t here. Okay, this guy evolved to this thing, and these alphas depend exactly on the time and on where these edges are, the Hamiltonian.
Right.
Yes.
Alpha is sorry.
Alpha
is be a matrix, shouldn't it? I mean,
alpha should be
a matrix in the sense that you go from if you start in 1, you go to all these states. But if I start in 2, after time t, I would be in another position. So that means that alpha is not just alpha 1, it's alpha 1, 1, and alpha 1, 2, and all.
Yeah. So these alphas also depend on the initial state.
Okay. So
yes.
But so these are things that you prescribe at t0, this matrix alpha, or
no. So at time t0, you're starting here. Right, and then as time evolves, because of these edges, this particular guy is going to evolve to this linear combination. These alphas, they depend on the time, on these edges, and they will be different if I have a different initial state. And these are numbers, complex numbers.
Yeah, but if I just go back to just a classical random walk, that when you just time stepping,
Yeah,
then I just prescribe a transition matrix,
yes.
and
Which
then
is the adjacent matrix of the graph with
it's
some
the
probabilities.
matrix and has a something one or yeah. You just get a Markov chain and you just step through the Markov chain and then I mean your stationary states are just the eigenvalues of this eigenvectors.
Yes.
But what so you're not going in discrete time here or
No, this is continuous time.
continuous time.
Yes.
And so what do you prescribe about the the stepping with the flow on these? I mean, so you have to prescribe something, don't you?
I guess that's the Hamiltonian.
Yeah.
This is so.
So the transition matrix is the matrix exponential of the Hamiltonian.
Okay, so if I move maybe to the next slide, this could become clearer.
Because Jay made a question about not having.
Yeah. Okay. So
Prescribe.
Right, yeah.
yeah. So this slide was coming. So maybe now things could be clearer.
Yeah.
Let's say this is the graph. This is a very specific graph, very small graph, 3 qubits. A is the adjacency matrix, and then you're gonna have an initial state here, for instance, or it could be anywhere else. And the Hamiltonian here, sort of, if you have an initial state which is just one vertex at ket1 and 0 everywhere else, then the Hamiltonian sort of boils down to this guy in this particular setting. And then you solve Schrödinger's equation, which is going to tell you if the Hamiltonian stays fixed, what happens when time moves forward. And this is the solution. And the solution is the exponential of I times the time times the matrix. And this, in this particular example, is exactly what it's going to look like. Now, these numbers are going to be the alphas that you were seeing in the previous slide. So if I start here, then the only thing that matters is the first column, because I'll be multiplying this guy by 1, 0, 0. And then the state is going to evolve to this alphas multiplied by the state, which is the ket1 in each one of these particular vertices and 0 everywhere else.
I have a question. Can you hear me?
Yes.
So at the classical random walk, is generated by the graph Laplacian. The graph Laplacian is both stochastic and Hermitian. So you could also use the graph Laplacian as the Hamiltonian. But here you use just the adjacency matrix. Why did you make this choice?
There's also a question being typed in here, which will be difficult. Do you consider? Yeah, another question. Yeah, okay. I'll try to answer both maybe. Yeah, so yeah, there are choices here for what kind of interaction I mean, this edge is representing what kind of interaction, and I'm choosing here one particular model in which these edges are representing polymatrices XX plus YY applied at these 2 particular qubits. One could have chosen a different model, and then it's going to depend on the physics you have in your system. And in different models, then the Laplacian is going to come up. So adjacency matrix is natural, physically speaking. Also, Laplacian is going to be natural, but different models, and they all occur, and they're all interesting both from the mathematical point of view and physical point of view. And also for the different questions, single particle, yes, my initial state is ket1 in one particular vertex and 0 everywhere else. We could have made the choice of actually initiating the thing with ket1s in more than one vertex, but then in a way that again I was not intending to go into that level of detail today. You could understand this multi-particle quantum walk as being a one-particle quantum walk in a bigger graph that you can define by saying, say, if you have K vertices marked 1, then you're going to define this bigger graph in which all the vertices are the K subsets of your initial vertex set. And then in this bigger graph, the quantum walk dynamics is going to be a one-particle thing. in this particular Hamiltonian choice. So we are not losing any generality if we restrict ourselves to this particular example. Hopefully
Somehow there's like an exact projection to a n-dimensional subspace
This is
where the
happening
true
here.
dynamics is 2 to the n.
Yes. Yes.
Okay.
These Hamiltonian is, I mean, this is the Hamiltonian that is defining these interactions is a 2 to the n by 2 to the n matrix, and the adjacent matrix is a 3 by 3 matrix, which is actually going to be a block in this 8 by 8 Hamiltonian. Yes.
Then you answer another question because Andre just asked.
This is, yeah, I answered this question with this, yes. I tried to at least, okay. Yeah. Should, yeah, I think I've covered what I was, yeah, no, I still wanted to, make this quite clear because every time again, someone says quantum analog of a random walk, you're left wondering, what exactly is this analog? And then the important thing here, even though the quantum walk and these guys, this shades of gray, they actually had a meaning, and the meaning was probabilistic. Again, they meant you were more likely or less likely to measure certain states in those particular qubits when you stop your random walk, quantum walk. Yes.
I have questions. Because so from the Hamiltonian, you define it red matrix, right? So the red matrix that you show, does that red matrix obey detail balance or it does not obey detail balance?
I think I didn't follow.
Because like I don't know about the quantum random walk, right? But like if you have a continuous time Markov chain in general, right?
Yeah.
Because you have continuous time here, and then you have the Markov chain and the
Sure.
mentioned. So the red matrix, like
Which matrix?
the red matrix,
Yeah.
the transition from one state to the other is so-called the red matrix, right? And for the classical,
Transition matrix.
Okay.
yeah,
Yeah.
and for classical walk, the red matrix satisfies detail balance. And I just asked you whether this detail balance also hold here or it does not hold.
What does it satisfy again? Sorry.
Detail balance.
The stochastic matrix in the classical case,
Yes.
but it is not in the.
Yeah. So what's gonna happen here is, this matrix here, it's unitary, right? If you take the absolute values squared of each entry, then it's going to be doubly stochastic.
Mm-hmm. And
Right.
then for that double stochastic, does it satisfy detail balance?
I'm not sure he knows what detail balance.
Oh, sorry.
Yes.
Okay.
Yes,
I'm
missing. Yeah.
I should start up. Yeah.
Well, maybe you explain what
Yes.
detail balance is.
So detail balance just means like the inflow and outflow of probability current is equal. So you're coming from another state to the current state, and from the current state out from the current state to the other state.
Yeah.
Does the flow we conserve or not conserve?
Yeah, I think I was about to comment on something that would possibly answer that question. So this matrix is unitary, and the state of the quantum system in a particular moment is going to be represented by a unit vector. So you have unitary matrix, and then you multiply by unit vector, you keep getting unit vectors. So this would be the analog maybe of what you're asking. The thing is, when you look at this picture, and these shades of gray, they are representing the probability of measuring things, then this is not working. It's not that if you have a vector which is giving like probabilities, and then you're moving the time, and then the state after a time is going to depend exactly on the probabilities before, what I would say is the Markovian property of a random walk. Then this is not happening here, right? So even though each time instant corresponds to a probability distribution, the state of the system is not exactly probability distributions being evolving as they would in a random walk. And the fact is, again, this is unitary matrix, unit vectors. So you keep having unit vectors happening time after time. However, you must take into account that the coefficients are not probabilities, they are complex numbers.
Yes, but normally you multiply to the conjugate, right, to transform it to probability.
Yeah. So you could do that, but then the quantum walk is not going to be what a random walk would look like with these probabilities. In the sense that if you're in a particular time and you have a probability distribution of measuring this guy, and then I don't know, time passes, it's not going to be a double stochastic matrix multiplied by that vector, giving the probability distributions of the new thing. You first have to go back to the real quantum state, which is a unit vector, apply the unitary matrix, and then recover the new probabilities. Yes.
Is it
yes.
not true that if it satisfies the built balance, then you don't necessarily have steady state?
No, when you satisfy the equivalent, then the steady state is Boltzmann distribution. But if you don't satisfy that, you don't know what exactly is a steady state distribution.
But I think he showed there was no steady state.
Yes.
So,
So it cannot be detailed balance.
okay.
But I think it's not relevant because it's that at every time there is a probability distribution of like what is the probability at every single time. But these things are not related to each other directly. They're only related to some complex matrix. So it's not like you get to evolve some probabilistic process over time. And every time there is a probabilistic process that is not related to the probabilistic process of the next moment. Okay, so that's why there's no convergence.
Thank you.
Even though it could satisfy the stage of balance thing at some time. But it just has no implication for a later time. Okay?
Thanks.
Well, so hopefully this has convinced everyone that the quantum walk is truly happening in these coefficients. I mean, what do they actually look like? I mean, this is the matrix. The matrix that was here is the matrix that we actually need to understand to see the quantum walk as it should, instead of those shades of gray moving that probably bothered you guys a little bit. What exactly do these entries mean? And is there some sort of nice dynamics or quantum walk in these entries? So this was mostly my goal today, was to show you some nice pictures of what the quantum walk looks like if you focus on one particular entry here. So this, let's say this entry here is going to tell you, is going to describe to you what's happening if you start your quantum walk in one particular vertex and you are observing what's happening in a neighbor, okay? And then actually, we got curious at some point, and then we decided to plot this. So this is going to be a curve in the complex plane as time moves forward. This is going to describe a trajectory in the complex plane. And then this is actually what it looks like for this particular entry here. Okay, in that particular graph, as time moves forward, as you can see up here. And then the curve starts to go over itself in this particular case. So this is more like what a quantum walk should be regarded as. Okay, so again, this particular entry is telling you what happens if you start here and you're looking what happens in this guy. Of course, if for each of these complex numbers, you take the absolute value squared, then you would be seeing that shade of gray moving darker or clearer as this number is approaching zero or moving away from it. But in fact, there is a complex dynamics here. This is what it would look like. So this is the graph in which three vertices are all attached to each other. And this would be what it would look like in the graph where six vertices are all attached to each other. So there's clearly a...
It's a tulip.
Huh? Yeah. Yeah. Unfortunately, none outside this time of the year. But yeah. It's actually the second time I come to visit Amsterdam, second time in February. So I'm clearly doing something wrong. So this is 6 vertices all attached to each other, and this is what the quantum walk would look like. So of course, we can already guess that for any sort of graph with all vertices attached to each other, the thing is going to look like this nice curve going over and over again. Now, this is the next kind of graph that we bother looking at the picture. So this is, now I have 5 vertices, but they're not all attached to each other. They're like a sort of like ring or cycle graph. And then again, I'm looking at what the curve looks like if I start here and I ask what's happening in the neighbor. So the 1-2 entry of the transition matrix. And then it looks like this. Which was good news because it seems to be something funny going on. After a while, this is what it looks like. But if you really let it go, then it's actually going to be dense in this region, though with different sort of like densities, as you can see here. And this was great when we looked at this picture because we're like, well, there must be something interesting here for us to work with. I mean, first of all, clearly there is a 5-fold sort of symmetry here. Is that is that connected to the 5-fold symmetry of the graph? I mean, that seems to be the obvious. It's not actually. It's just a coincidence in this particular case. And then there are many questions we do not know how to answer. I mean, we know that this is going to be dense in this region. So pick any point, you're going to get arbitrarily close to that point if you let time goes long enough. We do not know, I mean, even though this is a very small graph and the numbers are not too complicated, we do not know if this thing, it started at 0. We actually do not know if it actually goes through 0 exactly ever again, which seems to be a very natural, immediate question to ask. I mean, it certainly goes through points, certain points many times over because this curve is self-intersecting many times, but we do not know if it actually touches 0. That would be a first open question, though maybe not very interesting from the application's point of view. Yeah. So these are all the 3 pictures you would get from this graph. Why 3 pictures? Because you can start here and ask what happens in the vertex itself, and this is the picture. This is if you start here and you look at the neighbors, and this is if you start at 1 and you look at the non-neighbors. And then of course, there's a symmetry here. It doesn't matter where you start, it just matters if you're looking at the vertex itself, neighbors or non-neighbors. And these are the 3 pictures, and they're all, I mean, from my point of view, quite interesting. Just to convince you guys that the symmetry of the graph was not really the main thing there at play. This is another graph, also with a very clear 5-fold symmetry. This, however, are the pictures you get from the quantum walk. I mean, no 5-fold anything here. Actually, it's not even a curve being dense in the region. It's more like a curve going over itself many, many times over. So this actually is more related to the fact that the eigenvalues of this graph are integers, whereas the eigenvalues of this graph are not. So you get this sort of different behavior. Okay. This is an old friend of us graph theorists, the Peterson graph. Yeah, let's move forward. There's some more pictures. Just so, I mean, you wouldn't expect, you wouldn't guess what the pictures look like if you look at the graph. This is, of course, I mean, all 3 different things you get if you start here and you look at the vertex itself, this neighbor or these neighbors, right? So 3 different behaviors. And then the interesting thing is I've been looking at this quantum walks for a while. We knew some things about it, and then I was giving a talk a while ago, and then also showed these pictures in the talk. And then I was like, well, it would be very nice to have a nice mathematical description of what these curves look like. However, I don't know how to do that. And then fortunately, there was this guy in the audience, and then after the talk, he approached me, he was like, yeah, I think I know how to do that. And then we exchanged a couple emails, and the thing was really picking up, but then didn't really have a I mean, there was some nice math describing the curves, but no new theorems. And then after a while, and a while was like 3 years, I had a master's student, and then we developed this computational routine to describe very precisely what's happening when the eigenvalues are not integers. And then I went back to these pictures like, whoa, now I can actually compute them. And then I sent the email to this guy after 3 years, say, hey, sorry, I've been silent for a while. I have a preprint in which we're all co-authors now. And then he was very happy. We end up proving some nice results about these things. So let me explain very briefly what we can say about these pictures. So this is the graph again. This is the adjacent matrix. The adjacent matrix admits a spectral decomposition into eigenvalues multiplied by projections onto eigenspaces. And then you look at the transition matrix of the quantum walk. Let me actually check the time. Okay, I think I'm fine. The transition matrix of the quantum walk, and then of course you still have the same projections, but now your eigenvalues have changed. They're now unit complex numbers. You're looking at one particular entry, the 1-1 entry, let's say. So I'm just A0 is the 1-1 entry of this projection, A1 is the 1-1 entry of this projection, just to make the notation slightly easier. And then this curve is actually described by this function, which is a function on the parameter t. Okay, so this is e to the I, t, the parameter, eigenvalue theta 0, and a number a0, which is a real number. And then this is describing this particular curve. Now, yeah, okay. So what is the mathematics behind this? So you have a parameter t, which is a real number, and then what you're really doing, you're multiplying each one of the eigenvalues by t, and then you're asking what happens when t moves forward. So of course, this theta 0, theta 1, theta 2, they're going to be appearing up there. And then of course, every time t theta 0 moves 2 pi forward, you're back where you started. So you're actually mapping this thing to the three-dimensional torus, right? In which this thing has a period of 2 pi, right? This map. And then, so this is a curve. So you're starting with the real parameter t, and then you're mapping this curve to the three-dimensional torus. In this particular example, of course. And then from the torus, you're getting these 3 points, alpha 0, alpha 1, alpha 2, and then you're mapping them back to the complex plane by simply doing e to the I alpha 0 times the a0, the number, the real number. So yeah, so you're moving from a real line to a curve in the torus, and then you're mapping this curve in the torus to the complex plane. So this sort of describes this two-step process. And then for all graphs, you have a linear relation between, at least one linear relation between the eigenvalues, which is the all sum to 0, because the trace of the adjacent matrix is 0. So in fact, in this particular example, you have 3 eigenvalues in the three-dimensional torus, but you have one linear relation. The image of this curve is actually contained in a two-dimensional torus in there. And this is basically what's happening here. So you start with a t, and then you're mapping to the three-dimensional torus, and then you start moving, right? In this three-dimensional torus, I have no idea if this is the right direction, but anyway, you get the gist. And then this starts getting denser and denser as this parameter moves forward. And this is actually what this is going to look like, a bunch of sheets in this three-dimensional torus, which is a two-dimensional torus within. Okay. So this is the first step. The time t maps to this dense curve in this two-dimensional torus, which lives within the three-dimensional torus. And then you are sort of like scratching this into the complex plane. Okay, so this is exactly what's happening here. So this region is the image of this sheets to the complex plane by means of this function, which of course depends on the graph. So actually, if you simply drew the grid in this two-dimensional torus, this is the image of the grid. Whereas this is the image of the curve, because the curve is a bunch of lines getting denser and denser in this region, right? And this is quite nice because this gives us a almost full conceptual description of the quantum walk. And this pretty much happens to all graphs, except that if the graph is much bigger and you have much more eigenvalues, you would be in principle in a very high dimensional torus with this slightly lower dimensional torus within it. And then when you get the whole thing and you put it in the complex plane, if the dimension is too high, then you won't really see interesting things. You're just going to see like noise in the complex plane. So you get to see nice pictures such as these and these if you're moving from lower dimensional things in which this like sheet sort of like folds itself into this nice way. You can still get to see these crests and cusps. If the graph is much bigger, then you are less likely to see a nice picture in the complex plane. You still, however, have a very nice dynamics in these high dimensional toruses. So
that noise will still be dense in some region.
it is going to be dense, certainly,
Is the
because
region itself still nice?
it could be
Does it cover the
nice.
whole thing?
I mean, no, it could be not. It would be certainly more interesting. The image of the curve in the torus might give us some hope of understanding the quantum walk nicely. When you have the dense, I mean, it could be that the thing is actually just one dimensional if the eigenvalues are integers, say, as one of the examples I showed before. If you have like dense regions, then yes, they will sort of like help you understand what the quantum walk could look like. However, if this is, I don't know, 10-dimensional thing, and then you're like still mapping this 10-dimensional space to the complex plane, then you're going to have so many things folding on top of each other that you won't really see in the complex plane like these nice cusps. I mean, and when I say you won't see, it's like your human eye won't be able to see.
It's not a silhouette.
Yeah, no, there's still going to be, of course, I mean, it has to be contained in this like one-dimensional ball, right? So it has to be contained here. And yes, there's going to be a silhouette, of course. I mean, yes. However, I mean, here, quite clearly, there is a curve, which is only one curve doing this. The silhouette in a more complicated thing could be actually two different curves or three, and then you wouldn't really understand what's going on. I mean, you could, in principle, you can compute these curves, and this is actually something we did for cycles on the prime number of vertices in which you tend to get pictures that look nice. We actually were able to compute these curves explicitly. So there are two curves here, the red one and the blue, right? Which are describing these things. And we could prove the full rotational symmetry, and we could compute these caustic curves, which are the singularities of this map from this region in the torus to the complex plane. But in general, I mean, for bigger graphs or graphs in which you don't really have a very good understanding of how the eigenvalues relate to each other, then the things are not so interesting. And this is the paper that we did that, among other things in the paper. But this is certainly the good-looking part of the paper. Yeah. Let me just very briefly tell you about my favorite open question. So Fernando said it would be nice to talk about a recent paper Kristen and I put out with some open questions. And this is my favorite open questions in the topic of quantum walks in graphs. So there is another graph, and if after some time t, the state moves entirely and completely to another vertex of the graph, then this is called state transfer, or perfect state transfer. And here again is a representation of it in this cube, right? So after time pi on 2, it actually moves all the way to the other side. Of course, if time kept moving, it would move back. So there is an oscillating behavior. It's not converging, it's just oscillating from one side to another. And this is being studied for a while. So for instance, in this very simple graphs, you do have perfect state transfer between the end vertices. So you start here, you end up here after that time. You start here, you end up here after that time. This does not happen if you keep increasing the size of the graph, fortunately, because then it gives us a very rich source of problems to work with. So this doesn't happen for long paths, and this is a result known for a while now, 20 years. And this is given rise to a lot of interesting results in the connection between quantum walks and combinatorics. So for instance, if you want to have this state transfer between vertices which are combinatorially far apart in the graph, this is a construction that you could make. You start with a graph that admits the state transfer, and then you compute these products, and then the vertices corresponding to this product graphs will still admit this state transfer. I mean, after a certain time, a quantum walk starting here will end up here. Same thing here, a quantum walk starting here will end up here. However, these graphs are very annoying to the physicists because very quickly they become very large. And each one of these guys is a qubit. In a quantum computer that tends to have only a few dozens of qubits. So they will say, oh, this is useless. I mean, don't give me the next step because it's not possible to implement that. However, you could still be interested in the question. I want perfect state transfer between vertices which are combinatorially far apart. How big the graph must be to allow that to happen? I mean, as I said, it doesn't happen in your official candidates, which would be these linear chains. And the obvious construction is clearly giving you an exponential growth in the size of the graph compared to the distance, the combinatorial distance between these vertices. So yeah, this is basically the question. This is my understanding. This would be right now maybe my favorite, certainly, and one of the most difficult questions in this interplay between combinatorics and quantum walk. So how large must the graph be for you to get this complete nice state transfer from one vertex to another? I proved a very simple lower bound, which is a cubic function on the distance, using some elementary methods in spectrograph theory. This is short paper, very simple, straightforward result. And Alistair Kay, colleague, by using some very clever quotienting arguments, he could actually improve on these examples by showing that some of these vertices could actually be identified together in weird ways, but still couldn't get rid of the exponential growth. So the best known constructions are still, the graph is exponentially big compared to the distance. You have a lower bound, which is cubic. So obviously there is an enormous region here for you to get some improvement, right? Crystal, Vincent, and I are currently collaborating on an attempt. I mean, we're not really improving on this particular problem. We are relaxing a little bit our restriction of the state transfer being perfect. If it's no longer perfect, then we have some nice things to say about graphs which are much smaller and still admit what's happening. So this is the open problem that I wanted to just announce here in the end. And that's it. Thank you.
So maybe something I missed is the way things evolve on the graph directly related to, so I mean, is the A directly defined by the graph structure? So can you have the same graph structure and different definition of A, or A is always defined by it? I mean, a matrix A.
Yes, no, the matrix A, as I was basically doing here in this talk, it's always the adjacent matrix of the graph. So it's a 0, 1 matrix that tells you where the edges are and where they're not. You could, in principle, allow for certain variations of quantum walks in which, for instance, an edge has a weight. So instead of a 1, you have something else. This certainly makes some things easier. So for instance, in that particular case, if you allow yourself to put weights of arbitrary size, then you actually can get prefix A transfer in these chains by putting some weights here, which are going to be, but these weights, they are, I mean, there is a way, in a way, this graph here sort of corresponds to a weighted path with 4 vertices. So this is 1, and then the neighbors are going to be the next vertex, and then the distance 2 are going to be the next vertex, and then this is distance 3. And then you're going to be putting weights in this linear chain, which are proportional to the number of edges, which are moving from one class to another. So in many senses, a weighted graph could be regarded as a bigger 0, 1 graph with certain regularity properties for this purpose here of quantum mechanics.
Because I was thinking that, I mean, in the classical sense, in the classical context, you can define
Different properties.
Yes, I mean, you can also define, I was thinking of your last problem, where you can define backward processes and combine forward and backward process to make sure to reweight your trajectory, such that you start from one point and you always end up in a single point at the end.
Right.
So you can create
You can
a process
sort of
that would be
control a little
related
bit.
to control too.
Yeah, no.
So something that could be.
Yeah, in principle, you can. I mean, you can choose some weights on the adjacent matrix, or as someone asked during the talk, you could, instead of using the adjacent matrix, you could use the Laplacian matrix, which basically allows you to put some things in the diagonal here and some minus signs. I mean, yes, there is some room to play with the matrix, but the nice interplay between combinatorics and quantum walks, then you can't really allow yourself to put like, so if you allow free weights, then you start now talking about different sort of math to solve the problem.
This paper you showed before, or was it Kristen Dow's paper?
Yes. Here, yes.
Yeah, so this is slightly different, like in the sense that are there additional interactions between the nodes or something? No?
No, in this particular paper, they're just defining this problem of perfect state transfer. They prove that it works in these 2 graphs, that it doesn't in longer paths, and then they present this construction.
Okay.
That it sort of boils down to that in that particular paper.
So what they call spin networks, there's no additional.
No, it's just this,
It's just
this exactly. So these are essentially the results.
Defining the agency matrix, and that's it.
Yeah,
There's
you
no
see
additional-
happening here. This is one of the results they have, and the other one is this product construction. And then they discuss some physics, but the mathematics is basically that. Yeah.
Yeah, a definition of non-perfect state transfer.
Non-perfect. Yeah. So here I'm requiring that this guy moves actually with probability 1 here. So here I'm taking the absolute value squared of each one of the entries of the transition matrix. And then after time pi on 2, I'm getting a 1 here. So non-perfect would be, I mean, you give yourself some room here. So instead of requiring probability 1, you could say things such as, well, I want this to get, say, arbitrarily close to 1, which in going back to those pictures would mean that that curve approaches the unit circle arbitrarily often or arbitrarily well, however, never touches it. Or you could say, no, I'm just satisfied if this is bigger than half, for instance.
So there is a probability that the last node will never become 1. A small probability.
Yeah, so non-perfect would be you would be satisfied if instead of this being one, this being something close to one, or at least constant, or at least bigger than half, or something of the sort. Right? So, yeah.
I guess in practice, you would also want to have it stay at one for a while, because you can never do instant measurements.
Okay, no, that of course doesn't happen. I mean, this will keep moving back and forth. There is only one instant moment in which this is one and this is pi on 2. At any other time, this is not going to be equal to 1. You could then ask, looking at those curves approaching the unit circle, if they are too if it's a sort of like a cusp, I mean, if it's moving or if it's like a sort of like rounded thing that would allow you to have some error.
Exactly.
No, you
You
could
wanted
do that.
to stay within epsilon of 1 for as long as possible, so that you could
Yeah,
actually, with
yeah.
some certainty, extract the state.
No, you could do this sort of work. I mean, there are some papers that actually devoted a couple sections into looking at graphs with perfect state transfer that will be less sensitive to errors. Yeah, yes,
But those will be necessarily slower. Also means that you'll be slower leaving 1 in the first place.
Yes. But it is certainly it's an important thing to consider. Yes. There was a question.
With respect to, so if you want to implement this, I can imagine that this specific choice of Hamiltonian based on your incident matrix is not necessarily the one that is most easiest to implement in the quantum computer. So I understand that, this question arises from the kind of mathematics side, but is there also, like from the physics side, people investigating this more generally and maybe finding efficient implementations?
Yeah. So this is possibly the main motivation for this question, right? I mean, because we're trying to avoid having graphs first with many qubits, many edges, or second with many connections. I mean, certainly, let's say what I call the complete graph. I mean, all verses connected to each other. This is certainly not very desirable. So one thing could be, well, maybe I restrict myself to planar graphs that can be drawn in the plane without edges crossing each other, right? I mean, so there has been some experimental implementations of quantum walks in graphs. I mean, obviously, this has been done because they're too simple. But I mean, you can do like also these cycle graphs have been experimentally implemented. And yes, I mean, this is the moment that we talk to the physicists and they say, well, my equipment here only allows me to do like this connections or this many connections at each qubit. I mean, what can you do? I mean, yes, there has been some debates on what would be useful here, but certainly we don't want many qubits.
Is it interesting to combine it with measurements? You could imagine saying, okay, I'm going to measure 1 qubit so that I know that the state will be transferred.
Yes, you could do that. Yeah, in principle, you could like start your quantum walk, stop it, let's say measure, and then start again somewhere else. Yeah, the annoying thing of that is that you're introducing sources of errors, let's say, and interaction, and which is something you wouldn't want to do in principle. But yes, you could do measurement-based quantum walks, which allow you to sort of like hop. And then, so then this problem, of course, loses a little bit of motivation if you're allowing yourself to run measurements, because then you can hop from one to the next, and then you stop, and then from one to the next. Sure, yes. You had a question for Nelly.
Yeah, so I wonder, because you say you had a list of open problems, and some that is has inspiration with the physics side is the first passage time that is more generic than
the thing is, you have to be really careful when you define that, because what happens here is as soon as you start, you already have a probability of being anywhere. I mean, as soon as I press play, this guy has a non-zero probability. At instant, like any epsilon time, there is already a probability of being here. So you have to be very careful on how you define that. And the continuous time quantum walk, you have to put some thresholds. I mean, you want to like say, how long do I need to wait to be here with probability at least something? And then there's going to be graphs in which the probability is as the graph grows, the probability is upper bounded by something that goes arbitrarily small. So you really need to take care when you want to. So that's one reason why saying that a quantum walk is a quantum analog of a random walk is sometimes not that useful, because the usual questions you ask about random walks sometimes not really apply here the same way.
I was wondering something about this, so it makes me good with this point, that for my mind, I'm sort of missing a educational step in between the random walk and what you're doing, that is doing a discrete time quantum walk. Would that make sense in some way, at least to make sort of more of a connection to the classic random walk? Or why are we immediately going to?
No, that is a good question. Yeah. So in principle, you could say that the discrete time, is you could obtain a discrete time thing here by simply saying that you are only interested in discrete steps in this time t. However, when people talk about discrete time quantum walks, it's usually embodied with more structure. There is a coin thing happening at each qubit. There are some other unitary matrices different than the Hamiltonian. So instead of having only one Hamiltonian and one, say, dynamics, then you have more things intertwining which do not commute and add some movements in there. So usually in the community, discrete time quantum walks will not be simply saying that I want this time to be 1, 2, 3, 4. It's going to have some more structure. However, in which case it also doesn't have a very nice analogy from the random walk, because the random walk, you don't need that much structure to see the walker hopping from vertex to vertex. So in the quantum case, you'd say, oh, you hop from vertex to vertex, but also you twist inside. So in a sense, I'm not being that far away from the best analogy possible here, I think.
Thanks, Gabriel, again.
Thank you very much.